Hello everyone, guys, and welcome back to a new video. Today, after the official presentation of the Intel Core Ultra 200S processors, and after seeing the performance in general that this SKU is capable of from various reviews, I won't hide my great disappointment from you. Disappointment and questions about the path companies like Intel and AMD are taking. Now, aside from those processors in the 13900K and 14900K series, which have shown issues with oxidation and degradation that have triggered system instability, for all the others, I want to show you how the performance is absolutely comparable to the brand new CPUs in the Core Ultra 200S series, as well as the Ryzen 9950X. Specifically, referring to the Intel Core Ultra 200S series, I couldn't help but notice how the new production process and the new CPU chiplet design, produced by TSMC, the market leader, haven't had any positive effects except in terms of efficiency. But let me share a little anecdote. Here in Italy, we don't buy a Ferrari and then think, yes, but how much fuel does it consume? Now, unlike in previous videos, where I went back to overclocking my Intel 14900K CPU, in this particular case I stuck to the technical specifications of the Core Ultra 285K. So, P-Core Max Turbo Frequency, up to 5.5 GHz. Intel Turbo Boost Max Technology up to 5.6 GHz, Intel Thermal Velocity Boost up to 5.7 GHz. Finally, the E-cores are set to, by core usage, with the following configuration. When 3 cores are active, the multiplier will be for 6x, exactly as in the 285K. When 5 cores are active, the multiplier will be for 5x, and when all 16 E-cores are active, the multiplier will be for 4x. And just think about it, guys. What was the result? On Cinebench 2.3, there's a negative difference of only 1,000 points, with a score of 41,335. And in gaming, well, it goes without saying, the 285K is literally crushed. Now let's take a closer look at some benchmarks to get an overview of the potential shown by the 14900K with this particular configuration, and we'll compare it with the significant gap in the production process used on the 285K. If you enjoy the video, click on the bell to subscribe to the channel. Leave a like to help me create more specific content, and leave comments and suggestions to guide my future videos. So, on Cinebench 2.3, we scored 41,335 points. On Cinebench 2.0, we scored 15,600 points. Not too bad. On Y-Cruncher 0.8.5, we scored 45.7 seconds, honestly a time I've never reached until now. We are in the BIOS of the ROG Maximus Apex Encore, everyone. The first thing that stands out is the update to BIOS version 1703. Let's go to the Extreme Tweaker tab. On the Performance Preference tab, set ASUS Advanced OC Profile. On the AI Overclock Tuner tab, set XMP2. On the XMP tab, set DDR5 6000 MHz. On the ASUS Multi-Core Enhancement tab, set Auto Let BIOS Optimize. Finally, on the DRAM Frequency tab, set DDR5 7800 MHz. On the Performance Core tab, set by core usage. When 2 cores are active, we set the multiplier to 57x. When all 8 cores are active, we set the multiplier to 55x. We then move to the Efficient Core tab, where, again, we set by core usage. In the By Core Usage tab, we set Efficient Turbo Ratio Limit 1 to 46x when 3 cores are active. Subsequently, when 5 cores are active, we set it to 45x. And when all 16 cores are active, we set it to 44x. We go to the DG Plus VRM tab. For the CPU load line calibration parameter, we set level 3 as we take advantage of the higher droop output voltage drop, where undershoot and overshoot peaks are very small. This will result in less heat generated and a lower VOUT voltage. I should mention that this is directly related to the underclocking of the P cores by a full 300 MHz. We then move to the CPU Power Management tab. Here we adhere to all thermal limits set by Intel, so we set the CPU Core Cache Current Limit Max to 400 A. Power Limit 1 is set to 253 W, and in this specific case, since we have reduced the P core frequency by 300 MHz, Power Limit 2 is set to 300 watts. On the AC_LL setting, we will set 0.19 mom, while on the EADC_load line setting, we will set 1.09 mom, as we are using load line calibration 3. As explained in previous videos, the DC load line parameter informs the CPU about the type of load line calibration we are using in relation to the motherboard's electrical impedance. This allows the CPU to make the appropriate SVID request to the VRM. In my specific case, I have a ROG Maximus Apex Encore, and these values make my system stable. It should also be noted that to balance and perform the undervolt we're applying to the CPU, we will use the AC_LL parameter, which is the compensation parameter for the VOUT voltage that the CPU sends to the VRM itself. We will lower AC_LL by 1 mom at a time until the system is no longer stable. At this point, we will adjust the VF point on curve parameter 10, where, starting from an offset of plus 10 MV, we increase by another 10 MV until system stability is achieved. Having said that, let's scroll further down through the various settings and go to the *GIA VR voltage limit *, where we'll set our protection value to 1.5 volts. Essentially, if we make errors with the *GIA AC_LL* parameter setting, this limit will protect us from overvoltages that could damage the processor. We'll leave everything else on automatic. Let's exit. We move to the *VF point offset * tab. In this specific case, the first parameter I modified is the *VF point 10 * parameter, with a positive offset of 10 mV. In this sense, by applying a positive voltage to VF point #10, the processor protects itself and raises all voltages at lower frequencies. This is why, in all my videos, I've only shown current global SVID settings set to auto, precisely to leverage the CPU algorithm, which will surely do a better job than we would in selecting the ideal voltages for a given frequency and specific temperature. This allows me to be stable and efficient with less robust load line settings, such as LLC-3 and LLC-4, and achieve better performance than those who use voltage override mode. I only use this setting when I want to achieve the maximum in a benchmark at frequencies above 6.3 GHz, and not for daily use. After VF point #7, I set a negative value of 6 mV. In this specific case, I will show you how to achieve this value, which is not the result of random testing, but is obtained based on the Cinebench load database. Let's move to the Advanced tab. Under Platform MISC, disable Power State Express Native Power Management, and likewise, disable at SPM. Exit the Platform MISC Configuration tab, and go to CPU Configuration. In this case, disable Intel Virtualization Technology to enable the use of Intel Extreme Tuning Technology. Further down, among the various tabs, go to CPU Power Management Controller. In this specific case, go to CPU Power State, and enable CPU states. From the CPU Configuration tab, let's exit and move to the Thermal Configuration tab. In this specific case, we will enable Intel Dynamic Tuning technology. Then, shall we save and restart? Once system stability is achieved through micro increments of V, F.10, open ASUS Octal. On the CPU tab, go to V, F points. In the Target Die Sense tab, select the curve value you wish to modify, for example, 5.7 GHz. Set the desired value. Apply and generate the new curve. The application will also display a graphical representation of the newly generated curve. Then, take the new value obtained, -6 mV, and enter it in core domain on V at point. Next, test to see if you get any benefits, and if so, enter the obtained value in the BIOS. That's it for this video. Bye, and see you in the next video.